Oxygen is only about 21% of the air around you right now. So, why, when we talk about oxygen in the body, do we describe it as a pressure in millimeters of mercury instead of just a percentage? Okay, so now we're going to go over Dalton's law, and it's simpler than the name makes it sound. When gases mix together, they don't blend into one average gas. Each one keeps doing its own thing, and each one keeps exerting its own pressure, as if the others weren't even there. And that's what we call a partial pressure. So look at room air at sea level. Total pressure is 760 millimeters of mercury. Nitrogen is about 78% of that mixture. So nitrogen carries roughly 593 millimeters of mercury of that load. And oxygen is about 21%. So when you do the math, it's carrying about 159. Argon, carbon dioxide, and everything else account for the last eight or so. Add them up, and you're back to that 760 millimeters of mercury. The gases share the total, but every one of them keeps its own number. And that's your answer to the opening question. For gas movement across membranes, partial pressure gradients matter more than percentages alone. So let's put a number on it. The rule is short. The partial pressure of a gas equals the total pressure times its fractional concentration. So let's walk this through. Room air at sea level is 760 millimeters of mercury. We're going to times that by 0.21. So we're taking the percentage for oxygen and convert it to a decimal. And that gives you about 160 millimeters of mercury. 159.6 if you want to be like exact about it. That is the partial pressure of oxygen in dry air. And that actually matters when I said dry air. The moment gas enters the airway, it gets warmed and humidified. And remember, water vapor is a gas too, and it takes up part of the total pressure, which means oxygen shares drops a little. And we'll run that version a little later. Okay, now for some terminology, because um, this one can get a little tricky sometimes. You're going to see oxygen pressure described in three different places with three different labels. So you have PiO2, and the I is for like inspired, the gas being breathed in. And then you have P big AO2, and with the capital A, that usually signifies alveolar, and that's the gas down in the alveoli. And then you have P little a O2, and the lowercase a is typically reserved for arterial, the oxygen carried in the blood. Three locations, three numbers, and they are not interchangeable. Two gas properties that can get mixed up. We got density and viscosity, and they are not the same thing, and they don't matter in the same situations. Density is mass divided by volume. How much stuff is packed into a given space? And a denser gas is heavier for its size, and it's harder to push through a narrow or an obstructed airway. Viscosity is something else entirely. And viscosity is internal stickiness, right? A fluid's resistance to being deformed, like layers dragging against each other as they slide past. Density matters most in turbulent flow, right? So when gas is swirling and chaotic and molecules are colliding with each other, viscosity matters most in laminar flow. And well, that's when gas moves in smooth, orderly layers. And this is exactly why heliox exists. So heliox is helium mixed with oxygen, and helium is far less dense than nitrogen. Well, if you swap it in, the density of the whole mixture drops, which can reduce the turbulent resistance when a patient has an upper airway obstruction. And we'll sort through some scenarios and density and viscosity problems later on. Three variables determine gas flow. You have the pressure gradient, which we kind of covered already. The bigger the difference between 2 points, the more flow you're going to get, as long as resistance stays the same. The radius of the airway or tube, and this one's so powerful, we're going to give it its own section in the next video. So for now, small radius, very high resistance, dramatically reduced flow. Notice only one of these three has anything to do with the source. The other two are about the path and about the gas itself. Okay, so I want you to stop and think here and write this one down on your notes. Two gases move through the same narrowed airway. One of them is much less dense. Which gas is less likely to produce a severe turbulent resistance, and why? So here's the takeaway. Gases in a mixture share a total pressure, but each one of them keeps its own partial pressure. And that partial pressure is what the body actually responds to. Density and viscosity change how hard it is to move that gas, depending on how the gas happens to be flowing. Which raises the obvious next question. What decides whether flow is smooth or chaotic in the first place? And that is video 3, flow, resistance, and air entrainment.